In this video, we're going to take a look at an overview of probability distributions, which is going to be our topic of discussion over the next few lessons. And so I want to kind of make a connection for you between something that you've already learned and probability distributions. Earlier in the term, we talked about frequency distributions. And a frequency distribution allowed us to take raw data and organize it into a table form. And then we used that table, once it was organized, we used that table as a jump start for creating bar graphs and circle graphs and histograms, for creating some of our graphs associated with statistics. One of the key things about a frequency distribution is that a frequency distribution shows what actually happened when you conducted your experiment or when you collected your data. For example, if we think about our experiment as being that we're going to roll a die 20 times. And then we roll the die 20 times, and as we do that, we record how many times we roll a 1 or a 2, a 3, a 4, a 5, and a 6. So I did that, and so for example, I had the number 1 occurred twice, the number 2 occurred 7 times, 3 occurred twice, 4 occurred twice, the number 5 occurred 5 times, and the number 6 occurred 2 times. And so this is our frequency distribution. This frequency distribution shows what actually happened when I rolled the die 20 times. Okay, so we've talked about that previously. Well, now we're going to shift gears and we're going to talk about probability distributions. A probability distribution is actually going to describe what probably would happen or what we should expect to happen based on an assigned probability for every possible outcome. So again, if we go back and we think about the example that we're considering here of rolling a die, okay, so when we roll the die, hopefully you realize that the probability for any number on a die is 1 out of 6. So you could have a probability distribution. We use P for probability. We had F for frequency earlier. I can still roll a 1 or a 2 or a 3 or a 4 or a 5 or a 6. And so if I think about it, there's one way to roll a 1 on a die, and there are 6 options. So the probability that I roll a 1 would be 1/6. Similarly, for 2, I would have one way to roll a 2 out of the 6 options. Probability of 3 is also 1/6. Probability of 4 is 1/6. Probability of 5 is 1/6. Probability of 6 is 1/6. So this kind of represents our probability distribution to show that what the probability is for each event. Now in this scenario, notice that it's the same for every particular value that we have. That's not always the case. So we could have expected, what should we expect to happen? Well, I should expect then, if I roll the die 20 times and 1/6 of those times I should roll a 1, 20 times 1/6 is 3.3 repeating. So I should expect when I roll a die 20 times, I should expect between 3 to 4 ones, or I should expect to roll the number 2 3 to 4 times, 3.3. So that's why I'm saying 3 to 4 times. And so the probability distribution gives us that sense of what should happen in theory if everything works the way that it's supposed to. Now, we know in the real world that things don't always work exactly like they're supposed to. And so we have to take that into consideration. And again, a probability distribution can be written as a table, as I just showed you. It can also be, we can create a graph, and we can even use a formula. There are actually two different types or two different categories of probability distributions. And it's a similar breakdown to that of our variables that we talked about earlier in the semester. You have discrete probability distributions, and with discrete probability distributions, just like with discrete data, you have a countable number of possible outcomes. Again, think about the example of rolling the die. We have 6 possible things that can happen. So that's a countable number of outcomes. If you use an example of flipping a coin, there are 2 possible outcomes. So you have, with a discrete, you have a countable number of possible outcomes. They're typically going to be whole units, like a 1, a 2, a 3, heads or tails. You're not going to have overlap between those different outcomes. The probabilities for those particular outcomes are determined either theoretically, there's you got a 1 in 6 chance of rolling the number 1 on a die. You have a 1 in 2 chance of flipping a head when you flip a coin. Or you can also do it by observations, where you perform the experiment a number of times, like 1,000, 2,000, 3,000 times, and you base that probability on your observation. Again, we can represent that discrete probability distribution either in table form or in a graph form. But the primary characteristics of a discrete probability distribution, I guess there's really 3. One is you have that countable number of possible outcomes. 2 is the sum of the probabilities in the sample space. The sum of all the different things that can happen totals to 1. And then the third condition is that the probability of each outcome must be between or equal to 0 and 1. If you'll recall, we know that for probability, that a probability of 0 means that there's no way, no how that particular event is going to happen. It's impossible. Probability of 1 means that that particular event or outcome is certain, without a doubt, going to occur. And then we have any value in between that. And I can even show that to you. If we go back to our example of rolling the die, we have our outcomes. There's a countable number because there's only 6 sides on the die, so we have 6 possible outcomes. Each individual event, probability of rolling a 1 has a probability of 1/6, which is between 0 and 1. Probability of rolling a 2 is 1/6, which is again between 0 and 1. So if you look down through there, 1/6, as I just said, is between 0 and 1. So we meet that condition. And the third condition is that if we add up all of these probabilities for all the different things that can happen, and there's only 6 things that can happen, if we add this up, 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6. We have 6 in the denominator, and we have 1, 2, 3, 4, 5, 6 in the numerator. So 6 over 6 is 1. So when you total up the probabilities, this is saying the sum of the probabilities is equal to 1. So we meet the conditions of a discrete probability distribution. Again, if you want another example, if we think about the example of flipping a coin, okay? So if we have an example of flipping the coin, hopefully you know that when you flip a coin, that the things that can happen, the outcomes are you're either going to get a head or you're going to get a tail. And so if we think about that from a probability perspective, there's a 1 out of 2 chance or a 50% chance that I'm going to flip a head, or there's a 1 in 2 chance that I'm going to flip a tail. Again, I have a countable number of outcomes. In this case, there are only 2 possible outcomes when I flip a coin. 1/2 for the probability for each of those individual events is between 0 and 1. And if I total those up, okay, 1 plus 1 is 2 over 2, which is 1. So again, the sum of the probabilities is 1. So again, I have a discrete probability distribution. The other category of distribution, probability distribution, is called a continuous probability distribution. And a continuous probability distribution has an infinite number of outcomes between any 2 intervals or any 2 given values on an interval. Remember, we think of it as a continuum. We talked about this with continuous variable, how that, like on a measuring stick, it's not just 0 and 1. We can break it down into halves or quarters or eighths or 16ths. Okay, so you can kind of fill in those gaps. And so you have an infinite number of possibilities. For continuous probability distributions, typically those probabilities are determined theoretically, possibly even using a formula. Again, we can represent those in a table form or a graph. And the 2 requirements are very similar, but the terminology changes slightly, because when we start thinking about a continuous probability distribution, we begin to relate that to the area or the amount that is under the curve or the graph of that particular distribution. And so instead of saying the sum of the probabilities is equal to 1, we talk about the total area under the curve being 1. And then the second one, we still have the condition that the probability of each outcome is between 0 and 1. And visually, that would mean that the height of the bars on your graph are between 0 and 1. Now, there are a number of discrete probability distributions and a number of continuous probability distributions. We're not going to be able to discuss all of them. Some of the more commonly used discrete probability distributions are the binomial, the Poisson, and the hypergeometric. For this course, we're going to focus on the binomial. If you continue on and take the second statistics course, you'll talk some about the Poisson as well as the hypergeometric. You can actually take an entire course on discrete probability distributions. So again, because this is a survey course, we're kind of picking and choosing what we talk about. For continuous probability distributions, we're actually going to touch on all of these that I've listed here. Neither of these lists are exhaustive, but these are some of the more commonly used ones. For continuous probability distributions, we're going to be taking a look at the normal distribution, the student's t-distribution, the chi-square distribution, and the f distribution throughout the remainder of the semester.